Hello, I'm Jyotirmoy Sundi. I'm going to talk about reinforcement learning and how to scale RHLF-based systems for distributed learning across multi-GPU environment. There's a lot of improvements you can see recently in the models, either the Sonnet models or the OpenAI models, where they have done a lot of instruction-based RHLF-based models, which continuously improves the performance of these models. And I'm going to talk about the challenges there and also the core capabilities that are being used to build these platforms and systems. So the agenda to talk is a little bit summary about our reinforcement learning from theoretical frameworks to production systems, the foundations, distributed RL, what are the challenges involved there, then the RHLR principles and the practices that are normally applied in a production systems for training or for inference. The cloud native architectures, mostly these systems are trained on Kubernetes with multi-GPU setup with proper networking using NVLink. And I'll also talk about some of the scaling frameworks that I've used, so mostly on Impala, really, Lightning AI, DeepSpeed, some of the modern frameworks that are being utilized, and the challenges of monitoring and deploying these pipelines at scale. So reinforcement learning, the previous version of RL-based systems came from MDP. It's called Markov Decision Process, where it was more of a sequential-based learning algorithm, where it can maximize the cumulative reward at each step. But with deep RL, deep neural networks now, there's transformer-based networks. It can learn deep processing power, how the input gets transformed is it's more sophisticated with the transformer-based networks compared to just a sequential process in MDP. So it can learn much more sophisticated functions and multimodal, either be text, image, or video or audio. So the foundations of distributed reinforcement learning it can be either done in a multi-node, multi-pod system where there'll be a main server which will accumulate all the weights as the system learns throughout each epoch and each batch. The core challenges there are networking. How does the workers where the learning is happening, how do they communicate along with the servers, and how does the server accumulate all the weights to make sure the weight of the entire network is updated after each learning event. Now, there are different kinds of loss functions and policy optimization algorithms that will be applied, like PPO or GRPO, DDPO. These are the different kinds of policies that are mainly applied. There's also the actor critic models where you learn from examples, and these examples are either hand labeled or it can be sometimes generated by the machines itself, so that user becomes a continuous learning feedback loop. So learning can happen in multiple ways. One is the most common is from human feedback, and that is called supervised fine tuning, where you have a pre-trained model that you train on a large cluster. But then on top of that, then you have to fine tune it based on your own instructions, which are a basic set of questions and answers for LLMs. For vision models, it can be the image and the labels itself. So these are human labels, and these are created by experts in specific domains. For example, doctors or physicians or math Olympiads. They create this very high quality data set that can be used for supervised fine tuning, and that improves the performance of these models. So to train this data at scale, you have to also make sure you have a reward model or reward function defined so that the entire network can optimize for that reward function. The policies that you can apply for achieving the reward functions are, like PPO is one of them, as I mentioned. There's also DPO and GRPO. And all these policies depends on a data. Like some of the policies can do much better than the others, depending on the type of the data set and the reward functions you have defined. So you need to be very careful in defining the reward functions, because there are challenges involved. There are reward hacking. If the functions are not defined properly, the model might try to do if you can hack the reward function, and it might lead to consequences which are not desirable. So distributed implementation of RHLF, there is one of them. Most of them are trained on different kinds of large Kubernetes clusters, and there are different kinds of frameworks. Each of them has their own advantages and disadvantages. But the most common is data parallelism and model parallelism. Data parallelism meaning the same model weights is distributed across all the pods in the cluster, and the data, if it's very large size, it gets split across those nodes, and the learning happens in each the individual pods, which are then accumulated, and the workers which learns after each batch, it sends the weights back to the server, and the server accumulates those weights, and the neural network weights are updated and is sent back to the workers. There is gradient accumulation strategies. There are various kinds of accumulation strategies that can happen on the server pod, which is the main pod, which is monitoring all the training and learning across all these worker pods. And you also have to make sure the models are checkpointed because some of this training can take a long time to train, weeks to train. And sometimes you don't want to restart the training after let's say 50% of the training is done. You want to make sure it can restart from the checkpoints so that it can minimize the compute resource that is needed for the entire training process. Human feedback collection is one of the other challenges. So we have like human feedback. Sometimes the feedback loop can be very long. So depending on the use case, some feedback loops are faster to collect. Some feedbacks can take up to months to collect. So normally, generally, there is a lot of companies like Scale AI and Marker and a few others which helps creating this kind of labels based on human feedback. And if you create millions of examples, these examples then becomes a data set for training RHLF models at scale. And you can control the quality and also make sure the evaluation systems that you have are in line with the controls and the quality that you want to achieve after training, so that when it goes to inference, it can really highly perform compared to the previous models. The different kinds of cloud native architectures for distributed RL, I'll talk more about it. There are different kinds of frameworks that are there. But most of this is run on top of Kubernetes orchestrating all the pods of the resource management, the compute management, failover, recovery based on the checkpoints, replay buffers based on the actor critic paradigm, the stateful management of memory as well as the data. It can be in terms of sometimes in terms of terabytes. So all this state management has to be done and in a proper way so that it can restart or it can communicate the states across all these training pods for a consistent and reliable training run. Network optimization is another very important thing. Your network needs to be really optimized for this multi-GPU training. And NVIDIA has NVLink, which is really provides a highly optimal network so that the multi-GPU communications can be done at scale. And there are a lot of improvements that are going on for low latency communication across multi-GPUs so that it can reduce down the compute time when the data and state gets passed across these pods. There are different kinds of frameworks. Impala is one of them, Raylib is another, DeepSpeed is another. So there are different frameworks available, and each of these has their own pros and cons. And depending on the use case, you can decide what framework you want to use for multi-GPU RL-based trainings. Raylib is used if you have, it gives a lot of advantages of the components. There's some readily available components and metrics. It gives you the metrics of how the training is going like quickly out of the box. DeepSpeed is another one, which is normally used for very large scale transformer networks when you cannot fit the model in one GPU. Like the model needs to be distributed, the model itself needs to be distributed across multiple GPUs. So the learning happens across multiple pods and not just one pod. So we have for very large networks, you cannot have the entire model load in one pod. In that case, you need to have the model itself distributed across multiple pods. And the learning happens in a distributed way across all these pods from one part of the network to another part of the neural network. This is the example of GPU scheduling. K8 themselves don't by natively do the GPU scheduling. NVIDIA has device plugins, so you need to install them as part of the pod setup. And you can say, okay, how many pods, how many GPUs you want in one pod. Normally 4 is the number, but you can also go up to 8, depending on the resources that you have. And the distributed training frameworks where the training is actually happening. There are some of the things that I already mentioned. This Hoverboard is there, PyTorch DDP is there for data parallelism. There's DeepSpeed, which is from Microsoft. There's RayTrain, which is from Anyscale. And Qflow also provides PyTorch jobs and TF job operators where you can use them for distributed training. The most important thing is also when you're doing multi-GPU training is the communication. For fast communication, you need to use NVIDIA, the NCCL package to make sure the network is fully optimized for large scale training. So production deployment strategies, like we need to monitor all these various GPU uses because some of the GPUs, if the data is not properly distributed, some of the GPUs can really underperform. And so you need to have like very close monitoring tools. Like you can integrate with any of the platforms like Datadog and things like that to understand the GPU uses. And this needs some trial and error on understanding what is the right data distribution and sharding of the data that needs to be done so that all the GPUs are maximally utilized. And there's no like imbalance or high imbalance in terms of utilization of the GPUs when you're doing a distributed training. There are things like safety mechanisms for circuit breaker patterns for unstable policies. If there are pods that goes down, you need to have a failover and high reliable, like robust failover mechanisms, so that if a pod goes down, it does not break the entire training. It can recover from the specific checkpoint where it failed, and it can take it up from there, and then the entire training across the cluster can still continue. So it needs very optimal monitoring in terms of all the utilization across GPU, CPU, your network across the cluster, so that you have a good understanding about the utilization across when the training is happening, and you can optimize based on bottlenecks that you see. The bottlenecks can be of various types. It can be either network, it can be either data, or sometimes it can be like the model itself is learning slowly. So you have to make sure the learning parameters are set up in an optimal way, and you have to test and tune that multiple times to get to optimal learning for the entire model. So the loss can be the loss, and the loss function that you are applying, or the policies that you are applying, are really like improving the learning performance of the entire model. So there are a lot of things like learning rate parameters and all those things that also needs to be tuned depending on the type of data and the type of cluster that you have. So case studies for distributed RLs, there's most common use cases are large language models, which are commonly being trained using labeled data. There's SFT, which is I talked about supervised fine tuning, but also there are now new techniques coming up which are like reinforcement based fine tuning. And that actually can really speed up the training, because it's very difficult to get labeled data from experts like doctors, physicians, or Olympiads, mathematics Olympiads, or chemistry Olympiads. To get labeled data takes a long time. If you can define reward functions, and if you can define proper reward functions, the network can itself come up with new kinds of labeled data that can be fed back to the model. So in that case, you don't need a very large set of labeled data. You can have an initial seed, and that model can learn from that initial seed, and they can generate new kinds of data sets itself as part of the training, and that can improve the speed of your training, and you don't have to wait for a long cycle of getting human feedback data. So large language models is the most common use case. Is also use cases for autonomous vehicles and robotic applications where this data is being collected. For robotics applications, there are a lot of challenges in collecting data of images, but as you collect multiple various kinds of data sets, the model becomes more robust to new use cases. The challenges I'll talk about is human feedback scalability. Human feedback is the golden data set. So if you can get that data quickly and in a reliable way, in a very high, that's the most high accurate data. But that's the challenge. I think in the next 2-3 years will be needed to make sure the human data is collected across very special tasks that the model can learn and specialize on, so that the quality of the model can increase over time. Communication overhead is how do you make sure the policy parameters or the weight parameters are shared across the network in a reliable way, in a quick, in a fast way. So coordination needs a very high network bandwidth to make sure the coordination of these, as the model is training, the coordination of all these stateful data needs to happen in a very quick way, as that can become the bottleneck for your entire cluster and can increase the cost of your compute time. Then there are other challenges like temporal dynamics. How do you make sure your temporal dynamics in terms of the changing preferences are caught in the network? So that depends on the policy that you're trying to build, and also the loss functions. It depends on the network architecture as well. Then there are consistency guarantees and bias in representation, which talks about like how do you make sure that the model is trained. When it is trained, it gives consistent results and does not give very highly, like the certainty of the results should be within some bands, so that each time you train, it should improve. Because if you have inconsistency, then you cannot trust the model every time you train. So you have to make sure there's consistency guarantees in kind of data availability, the compute time that is needed to run, and consistency in terms of the model performance itself. When you're training it multiple times, it should give the same results, close to. It might not be exactly same because it's an undeterministic system, but it should be close enough. The emerging trends, there is also a new way of doing RHLF, which is federated-based federated-based systems, where that means the learning can happen on the edge itself instead of on a cluster in a Kubernetes pod. You can also do learning directly on the edge devices. There can be millions of edge devices where that can be the data that's collected, and the training happens. Some of the training can happen directly on the devices for privacy preservation, and then the devices then sync their learning the weights to a central server, which accumulates all the learning parameters, and then it merges it, and then it can send it back to the devices, so that you don't have to need to have a like very large training every time. Some of these continuous learning can happen on the devices on the edge itself. So that's a federated learning approach. There's a lot of research going on that area itself. Then there's multimodal, which is like image, audio, your text, video, and all those other things. There's automated feedback-based learning where you can collect the data automatically. And there is a lot of promise, a lot of companies are seeing where feedbacks are collected within the product itself, and either good or bad, and that can be used. And those labels that are collected from the product itself are then used either as a part of the training process while you're doing fine tuning with your instruction-based fine tuning with RHLF, or some people use that as part of the RAG application itself, where those feedbacks are used as part of the prompt, and then when they call the LLMs, those feedbacks are given as references for chain of thought reasoning. So the path forward, there is still a lot of work to do. I think that the way to do distributed RHLF, there are a lot of frameworks out there. But the most challenging part, I think, is right now the data collection part from researchers, engineers, like coders, or doctors, as physicians, or teachers, or any profession, any domain. So we need lots of data, I think high quality data that needs to be collected so that the model can continuously be trained with reinforcement learning with human feedback. And this feedback data are the specialized data gets collected. So that getting that at scale across all the people in the world, let's say 1 billion people, that can really improve the new versions of models that are coming out. Now, that might not be always possible to get. So that's why I think the reinforcement-based fine-tuning might be one of the new ways where with custom reward functions can be the new way where the model itself generates new kinds of data and hypotheses that can be used for training. But that's a lot of research going on in this area as well right now. So that's it. Thank you so much for listening to me. I would love to get any questions and answer them as needed based on my experience so far.